Hello, everyone. So it's a pleasure to have Marcin and Liz, who will speak about the Ising magnetization field. Marcin.
Okay, thank you, Piet. Thank you, Trish, and thank you, Subhajit, for the invitation. I'm really sorry that I cannot be in India right now. I hope you're enjoying the conference under these circumstances as well. I have the pleasure of speaking about a joint project with Thomas Alcalde Lopez and Lorca Hini. Lorca is with you over there. So if you have any questions after my talk, please approach Lorca. He will be happy to answer. The paper is already on the archive, and the main result that we prove is a new coupling between the continuum Ising magnetization field and the Gaussian free field. So this is the outline of the talk. So I will first define the Ising model again and talk about the FK Ising model and the related Edwards-Sokal coupling. So these are all classical things. I will recall them so that we have we touch on some common background. And then I will talk about already classical results about the convergence of the critical Ising magnetization field to the continuum object. And the continuum version of the Edwards-Sokal coupling. So that's a result of Kamiya, Garbaum, and Newman. And later I will talk about the GFF, which is also a classical and central field in the continuum. I will recall its definition, and I will talk a bit about a geometric object related to the GFF, which are the two-valued sets of the GFF. And then hopefully I will state the result. So that's the plan minimum for today. I will state our main result, which is a continuum coupling between the GFF and the Ising magnetization field, which uses these two-valued sets. So it's a version of a continuum Edwards-Sokal coupling where the role of these FK clusters is played by these two-valued sets. And then I will try to say something about the proof. So I will mainly focus on discrete statements or discrete identities in law. So discrete couplings between different objects, which is basically the starting point for our paper. And then if you have more questions about the proof, please ask Lorca. He knows it better than I do anyway. So if I have time, probably I don't have time, I will state some conjectures for the critical Ashkin-Teller model. And please interrupt me if you have any questions. All right. So what is the Ising model for me? I have a finite graph. And in this talk, I will just fix a single coupling constant J. Most of the statements in the discrete hold on any planar graph with any choice of coupling constants for any edge. So this is a simplification of the framework. I just have one coupling constant, and the standard Ising model is given by the Gibbs-Boltzmann distribution with the standard Hamiltonian, where we have pairwise interactions between spins joined by edges of the graph. And this is the so-called Ising model with free boundary conditions. I will mostly talk about the Ising model with plus boundary conditions, where I moreover condition on every spin on the boundary of the graph, if the graph is a planar graph, to be +1. So I will denote the measure by P plus. And here is the sample of the Ising model with plus boundary conditions. Okay, so we have seen already the FK Ising model here, but I recall the definition. So for the FK Ising, or the random cluster model with parameter Q equals 2, we choose the P parameter to be equal to 1 minus the exponential of minus 2j, where j is the coupling constant from the slide before. And now I define the FK random cluster model with the notation phi as usual by this distribution, where for every open edge of the configuration, I have a weight p, and for every closed edge, I have weight 1 minus p, and everything is, so this would be obviously the Bernoulli percolation model if it wasn't for this term, which is counting the clusters of the model. And here clusters are connected components of the configuration, where isolated vertices of the graph are also considered clusters. Okay, so that's standard here, a possible configuration of the FK model. And in this case, you see that everything on the boundary is in one cluster. So that's the wired boundary condition case, which I also denote by a 5 plus as in parallel with the Ising notation. Okay, so there is a famous coupling between these two objects. So the FK model was introduced by Fortanes Castelline, and they described its properties. But the full properties of this coupling that I'm going to describe now were, as far as I know, only first explicitly stated by Edwards and Sokol. That's why we call this coupling Edwards-Sokol coupling. All right, so it has two versions. The first one goes from left to right in this picture, which is from the percolation model to the spin model. So on the left, I have a sample omega of my FK model, and then what I do is I sample for every cluster symmetric and independent coin, and I assign the result to every vertex of the cluster, and I get a spin configuration. And the statement is that if you start with the FK model with these parameters that I just described, you do this procedure, you get the Ising model with the parameters that I described in the first slide. So that's the one direction of the Edwards-Sokol coupling. And the consequence of that, which is very famous, is a geometric interpretation of the two-point function of the Ising model. So we get that the expected product of two spins is just the probability that two vertices are connected by an open cluster of omega. So for plus boundary conditions, you can also speak about the one-point function, which is non-trivial. And in this case, this formula takes the following form. So the expected value of a single spin under plus boundary conditions is the probability that the vertex is connected to the boundary of the graph. So this is the simplest consequence of the coupling. And the most general consequence of the coupling is the following. I want to mention it for future reference. So if I have any subset of vertices A, and I consider the expected product of spins over these vertices, this is a simple exercise to check that this corresponds on the FK side to the probability that your percolation configuration is in this event FA, where this event is the event that every open cluster of omega intersects an even number of vertices from A. Okay, so that's a standard consequence. And what I want to say here maybe is that to completely characterize the law of the Ising model, it's actually enough to know all these numbers. It's also an easy exercise. Since it's a plus minus one valued field, it's enough to know all these first moments to completely determine the law of the Ising model. So on the side of the percolation model, it's enough to know all these probabilities. Or if you would like to have a percolation model which satisfies this Edwards-Sokol property, it's enough to check probabilities of all these events. Okay, and if they agree with the Ising spin correlations, you have a percolation model with the property that if you flip spins on every cluster, what you get out of that is the Ising model. Okay, I will also talk about this second direction of the coupling later on. So the second direction is if you start with the Ising model on the right, and now what you do is for every edge, which has at its endpoints the same spin, so either edges with two pluses or two minuses, you flip a coin with probability P, which is related to J in the same way as before. On success, you open the edge, and on failure, you keep it closed. You do it for every edge, you recover an edge configuration, which happens to be distributed as the FK2 model. So this coupling has two directions. Either you flip coins for clusters of the percolation model, or you open independently edges over a spin configuration, and you only open the edges which have the same spin. or the agreement edges. Okay, so what are the nice properties of FK percolation, as we already know? So it's a canonical example of a percolation model which has the FKG inequality, so positive association, which is very helpful if you want to work with it. In 2 dimensions, it has another special feature is that it's self-dual in the following sense. So in 2 dimensions, you can consider the dual graph. So you join every 2 faces of your original graph by an edge. Whenever they share an edge in the original graph, and you call this graph G star, it's the dual graph. And now you can, as usual, define the planar dual percolation model omega star, which is defined as a subset of the edges of the dual graph with the property that the corresponding primal edge is not there. So if I had my primal edge here, which was pink, I don't take my dual edge to the configuration and vice versa. Here, I didn't have a pink edge, so I can take this blue edge to my configuration, and that's my omega star. So the FK model is famous for its self-duality. So it's also an exercise, maybe slightly harder to check that if you start with an omega, which is distributed according to the FK model on G with coupling constants J, this dual configuration, omega star, will be again the FK model on the dual graph with the dual coupling constant. And the dual coupling constant satisfies the Kramers-Vanier duality for the Ising model, which is just this equation. And the boundary conditions change. So if you start with free boundary conditions, say on the primal graph, then your model will have wired boundary conditions on the dual graph and vice versa. So these are very nice features, which allowed people to prove spectacular results about the model, in particular in 2 dimensions. So now I will mention some classical now results about convergence of critical Ising. Okay, so what is the setup? The setup is I fix some continuum domain in the plane, and I approximate it by a graph, which is the subgraph of the square lattice with the small mesh delta, and I send delta to 0. I will consider here, for the sake of being concrete, the model with plus boundary conditions and the model at criticality, which for the Ising model happens to be the case, the point where this is an equation for the J critical. So J critical is the value of the coupling constant such that the hyperbolic tangent of J critical equals exponential of -2 J critical. So we consider the Ising model at criticality. And it's a landmark result from over 10 years ago by Chelkak, Ongler, and Zurov that properly rescaled correlation functions of the critical Ising model converge to conformally covariant scaling limits. In particular, if I consider the expected value of a single Ising spin in this delta approximation of D under plus boundary conditions, as I said from the Edwards-Sokal coupling, this is the same as the probability of being connected to the boundary. From the results of Chalkak, Ongler, and Izurov, it follows in particular that this thing behaves as the mesh size to the power 1/8. Okay, they proved much stronger result. They proved convergence of all correlation functions and with explicit limits of these functions. Anyway, 1/8 is the critical exponent for magnetization in the Ising model, and from this formula it follows also that it's the one-arm exponent for the FK, the critical FK model in 2 dimensions. Okay, so after these breakthrough results, some people started looking at the model from a different point of view. So you can think of an Ising configuration not just as a collection of spins, but as a generalized function. Okay, So I can think about an Ising configuration as a generalized function, meaning I can feed to it a test function f. So if sigma delta is my spin configuration on this d delta graph, I can feed a function f to it, and I will get a number out of that, which is just like a discrete Riemann sum or a discrete Riemann integral of the field times the function. And here is the scaling factor, which is also there, which corresponds to the scaling dimension of the one-point function. And I have to rescale everything by delta squared, which accounts for the quadratic number of terms in terms of the size of the domain. Okay, so I can consider a rescaled magnetization field, which is this object, and it acts on test functions in that way. And what Kamiya, Garban, and Newman proved is that this thing also converges in a proper sense in some Sobolev space to a continuum distribution, a continuum generalized function, which is conformally covariant, and so on. And they also proved that the field is not Gaussian, for example, which one doesn't expect in 2 dimensions, but if one does a similar procedure in dimension 4 and higher, this is known that the Ising magnetization field should converge or will converge to a Gaussian field, actually. So this is a different point of view on the Ising model. You don't think about it as a collection of spins or a collection of interfaces. If you think about SLE, for example, here you think about it as a generalized function. Yeah.
Marcin, just ask, why, how do they know it's non-Gaussian?
They study the tail behavior of the field, and they show that it has no non-Gaussian behavior. I don't remember what exactly the statement is.
Okay, thanks.
They prove that the tail is of the form exponential of minus x to some power, which contradicts the Gaussian tail, I think. Okay, so that's the statement of the result. Well, actually, if you know convergence of Ising spin correlations, and you also know RSW bounds on the FK model, this result is not that difficult to obtain. But maybe a more interesting question is, can you have a geometric version of that statement? Or in other words, does the Edwards-Sokal coupling survive in the scaling limit of the Ising model? And how would you go about proving something like that? So first of all, using the Edwards-Sokal coupling, I can rewrite my spin configuration thought of as a generalized function as the indicator function of the cluster of the boundary. So here I will consider, again, just plus boundary condition for the Ising model, which means that in the Edwards-Sokal coupling, I always put sign +1 for this cluster, and the rest is the sum of IID coin flips for every cluster, and then there is the indicator function of this cluster. Okay. So I just rewrote my Ising magnetization field according to the Edwards-Sokal coupling. And now I do the rescaling. Again, there is the rescaling of delta to the delta square, which accounts for the number of terms, and there is the magnetization exponent of the Ising model appearing. And I would like to take the limit of that. Okay, so basically we will need two ingredients of to make the statement rigorous in the scaling limit. The first one is we want to have some type of convergence of these clusters to an object in the continuum, which we'll call continuum clusters. It's not clear what they are right now, but it will be very useful to have convergence of the clusters themselves to a continuum object. And second of all, we have to have convergence of these discrete measures. So these things, without a sign, they can be thought of as rescaled counting measures on the cluster. And we would like to have a scaling limit result for those. And these two things should be connected in the way that this measure corresponding to a cluster should be supported on this continuum cluster which exists by one. Okay, so that's what they actually did. So Kamiya, Garban, and Newman, and there was a second paper of Kamiya, Konine, and Kiss 3 years later, which made this framework rigorous. So what they proved is that there exist measures in the continuum with disjoint support. So there is a countable number of supports, CK, and we think of them as these clusters in the continuum. And there is IID signs. And they have this property that if you consider this infinite series, okay, I have to say in which order I take this sum. Since it's infinite, you can order, for example, these clusters by their diameter in the continuum and consider this sign. They prove that this sum converges, and moreover, the limit is this critical Ising magnetization field. So they established a continuum version of the Edwards-Sokal coupling. Moreover, they provided us with a precise description of the law of these clusters, which I will hopefully now recall. And moreover, each cluster in this decomposition has a dimension which matches the dimension of the Ising magnetization. So the dimension is 2 minus 1/8. And also they proved that each of these measures that you get in the continuum is just a function of its support. So in some sense, it's an area measure. It's a continuum counting function on counting measure on these clusters. So it's a type of area measure on these clusters, and these clusters are obviously fractal. So these are fractal measures. Okay, but what exactly is the distribution of these clusters in their work? So to define that, I have to recall what the CLE kappa is. So this is a conformal loop ensemble. It's a collection of, it's a conformally invariant collection of loops in our domain. And they look differently depending on kappa, and they were defined in different works depending on kappa. So they were first defined for kappa between 8/3 and 4, for which there is an example on the left with the CLE4, in which case these loops are simple and they don't touch each other, and they also don't touch the boundary. So a version of that is a CLE4. And if kappa is bigger than 4, for example, 13/3, these loops will touch the boundary, which will touch themselves, and which will touch each other. So that's one of the differences between these ensembles. And the first type was defined by Sheffield and Werner using Brownian loops, actually, Brownian loop soups. And the second type was defined by Miller and Sheffield in their imaginary geometry works. Okay, so what type of set will be a continuum cluster? It will be actually the carpet or gasket. So there are two names. So the set of points contained, not contained in the interior of any loop is called, for kappa between 8/3 and 4, it's called a carpet, and otherwise it's called a gasket. So these are the gray sets in these pictures. So these will play the role of clusters for me in the continuum. And moreover, this is the more relevant example for now to compare with the work of Kamiya, Garban, and Newman. So why is that? If you recall the FK2 model and its dual, you can draw a set of loops on the medial graph which separates the two configurations. And it was proved by Kempinen and Smirnov that this set of loops actually converges to this collection CLE 16/3. Okay, so we know that in the discrete, the set of loops has the same amount of information as both primal or dual clusters. And we know that the in the discrete, the primal and dual clusters, they alternate between they're basically the space between consecutive layers of loops, which are alternating, okay? If you consider the nested set of loops, the spaces between the first layer and the second layer is the primal clusters, and the second layer and third layer are dual clusters, and so on. So it suggests that in the continuum, these continuum clusters should be somehow alternating gaskets of the CLE 16 over 3, which was actually, that's the thing that they proved. So if you recall the definition of this series, the first cluster was called C0. So it will be the gasket of the CLE 16 over 3, which is this pink region. And moreover, each next cluster will be a gasket of CLE 16 over 3 in some random domain, which is obtained from the nesting of the CLE 16 over 3. Okay, and it will be alternating nesting. So the whole picture, which is in the discrete, somehow carries over to the continuum, and the role of clusters is played by the role of these gaskets, and the fact that you alternate between primal and dual in the discrete will be seen in the fact that in the continuum you also have to sort of do 2 iterations of the CLE 16 over 3 to get to the next gasket. And yes, so the dimension of this CLE 16 over 3 gasket is known, and it matches exactly the one of that I mentioned before, and matches the magnetization scaling dimension of the Ising model. I forgot to put a reference here. No, I don't remember who actually proved that. Sorry for that. Okay. So that's the picture, and the question is, okay, what exactly are these measures in the continuum, in the discrete? They are just counting measures, and in the continuum, they are somehow area measures, and they are expected to be the Minkowski content of these sets, which is not proved. And if you look at the paper of Kamiya, Garban, and Newman, the most technical part is actually to prove convergence of measures and to prove that the measures that you obtain in the limit are actually measurable functions of these supports, or of the CLE 16 over 3. But the main takeaway of this whole story is that this Ising magnetization field can be constructed completely geometrically in the continuum purely out of these nested CLE 16 over 3 loops and these associated conformally covariant measures. So that's the continuum version of the Edwards-Sokal coupling. So that's not our work. So our result will be something like that, but with a different representation, which connects everything to the GFF. So what is the GFF? It's just a Gaussian field in the domain whose covariance is given by the Green's function of Brownian motion. And for me, the GFF here has Dirichlet boundary conditions, meaning that Brownian motion is killed when touching the boundary of the domain. And it's a centered field. Yeah, and the covariance is given by this formula. Okay, it's a generalized function, so it doesn't exist as a random function. We know about that. It's a central object in conformal geometry. It gives rise to many other objects. It gives rise to SLE curves through imaginary geometry. It gives rise to Gaussian multiplicative chaos and to Liouville quantum gravity. And as a result, as a consequence of our result, we'll see that it also encodes fully the scaling limit of the critical Ising magnetization field. So the GFF is really a central and universal object in planar conformal geometry, random conformal geometry. Okay, but so that's very well known. Maybe something that is not so well known is is the notion of two-valued sets, which I find to be one of the most beautiful things in probability. For my, that's a personal opinion, obviously. So even though the GFF is not a function, one can define a notion of level sets of the GFF. And so what do? You fix two values, A and B, and you think intuitively about, and you consider a GFF in your domain with zero boundary conditions, and you intuitively think about the set of points which are connected to the boundary by paths over which the field takes only values between minus A and A, okay? As here, as written exactly here. So that's an intuitive definition because the field doesn't have pointwise values, but you can make sense of that through a Markov property. And so you can define these things axiomatically by their Markov property with respect to the GFF. So the GFF will have a Markov property in the sense that this set of points connected to the boundary, it's connected, its complement will split into connected components, which are these lighter regions here. They will have boundaries, which will be loops. And inside each loop, the field will have, if you condition on what's outside, the field inside will be again an independent GFF with boundary values which are either B or minus A, okay? So in every loop, there is a value which is called a label, which gives you the level, the boundary conditions for the GFF inside that loop. And for these two valued sets, it's either minus A or B. And these things were defined by Aru, Sepulveda, and Werner, and they were later studied by Aru and Sepulveda. And we know quite a big deal about them, and we know their properties and when they exist and so on. So, for example, they only exist when A plus B is bigger than lambda, where lambda is a special value corresponding to the so-called height gap of the GFF. We know also that if A plus B is, they said correctly or not? Or should it be 2? Okay, now now I'm mistaken. Probably this should be 2. If we know that if A plus B is smaller or equal than 4 lambda, or strictly smaller, for example, these loops will always touch the boundary, or there will be loops, there will be boundaries of these regions which touch the boundary of the domain. So the gap, the total gap is too small, and the field somehow immediately jumps to one of these two levels from the boundary. So these sets will actually touch the boundary. And for this set of parameters, we know that these loops don't touch the boundary and they don't touch each other. And an example of this range is the boundary range, minus 2 lambda, which actually is distributed as the CLE4, conformal loop ensemble with kappa equals 4. So before I told you about CLE kappa, this is a family of conformally invariant loops defined through also some Markov property that I didn't mention. Here there is another collection of loops parameterized by these A and Bs, and they are also defined through some Markov property with respect to the GFF. So these are two different families of conformally invariant loops, and they happen to have a point in common, which is the CLE4. So if you have a GFF and you look at the set of points connected to the boundary such that the values stay between minus 2 lambda and 2 lambda, and you look at the boundaries of the regions which are in the complement, this will be again a CLE4. So that's a point in common between these two families, and it will appear in the statement of our theorem as well. So also these are somehow analogs of stopping times for Brownian motion. Okay, so a GFF can be thought of as a generalization of Brownian motion to two-dimensional time. So if you have a Brownian motion starting at 0 and you wait until it leaves the interval minus A and B, Well, the first time it leaves it, it's somehow this set of points connected to the boundary, which is here 0, such that the values are between minus a and b. Okay. In one dimension, Brownian motion is a well-defined function, so everything makes sense. Here, it's not so clear, but it can be made sense through this Markov property, and it turns out that these sets are relevant for the Ising model as well. Okay, so now that I have at least gave you some intuition what that is, I can have a first statement of our main result is that the Ising magnetization field can be constructed as a deterministic function of a single instance of a GFF and a family of independent coin flips, okay? Which in particular means we obtain a natural coupling between the Ising magnetization field and a GFF. And then maybe the main takeaway of this is that, okay, the GFF really seems to play a central role, and it even underlies the Ising magnetization field, which was not, I mean, this result, as far as we know, was not predicted before, so it may be surprising. Okay, a more concrete version of that is that we have a similar decomposition as in the Kamiya-Garba-Newman paper with the family of clusters, which are now different. We have a continuum family of clusters in the domain, and each of them has its own measure, mu. And okay, coin flips are the same, and the form of the expression is the same. We claim that this sum, oh, sorry, that was a big skip. We claim that this sum is again the Ising magnetization field. I will define these sets soon. And moreover, the measures are measurable functions of their supports, which are these clusters. And moreover, this full collection of these continuum clusters is a measurable function of a GFF. So if you give me a GFF and a family of coin flips, I can give you an Ising magnetization field. And actually what we prove in the paper is that there's 4 Ising magnetization field naturally associated with every GFF. I will just focus on one of them here. So maybe what is the takeaway from this statement is that there is something in physics called bosonization, which is a relationship between the GFF and the XOR Ising model, which is a product of 2 independent Ising models. And it's an explicit relation connecting the cosine of the GFF with the scaling limit of the XOR Ising field, or the sign of the GFF, depending on boundary conditions. So we think of our result as an extension of this statement because we actually give a coupling between the Ising itself, not the XOR Ising. And what is different here is that in this coupling, the Ising field is actually not a local function of the GFF as it is in the bosonization framework for the XOR Ising. These cosines and sines are local functions of the GFF. Here, what we have is a function, but it depends globally on the field. I mean, to know the level lines, it's not enough to know the field in your vicinity. You have to know it globally. So somehow it's an extension which fits with the framework of bosonization, because in the CFT of Ising, or in this CFT description of bosonization, the Ising field is something which is called the twist field of the GFF, and it's not a vertex field, so it's not a local function. Actually, it seems, okay, not that I understand the physics description very well, but it seems that the twist fields are fields which change the topology of the domain. So they are actually acting in a way that is not probabilistically easy to describe. And we actually have a probabilistic description of a field which is coupled to the GFF, and it is the Ising field. Okay, so what are these clusters? First of all, if you look at the Ising with the plus boundary conditions and you have a GFF in this disk, the first set that I take is the CLE4. So it's this two-valued set of with A equals B equals 2 lambda. And my first cluster C0 is just the carpet of this CLE4. So that's the set that gets sign plus in my decomposition. And here I sort of put the values of these labels for the loops, meaning that inside this loop the field has value 2 minus 2 lambda, and in this one it has value 2 lambda. Okay, and what you do later is you sample a different version of the two-valued set, and you see it that it also, I mean, we drew it, obviously it's not a simulation, we drew it in a completely different way. And what is the difference is the difference that the sum of the levels, the total gap for this set is actually 2 squared 2 lambda, which is smaller than 4 lambda. For this one, it's 4 lambda. So it's exactly here where we stop having loops touching the boundary. So these are the loops which don't touch the boundary. That's the CLE4. And inside we sample this set, which has a smaller gap, meaning that the loops will actually touch the boundary and they will touch themselves. So you can see it in this impressionistic picture. And now we also put the labels of the field inside. So if you add, so if this loop had value 2 lambda of the field, and you add minus 2 lambda, you will go down to level 0 of the field. And if you add this value, you will go, okay, you will go up to level 2 squared 2 lambda. Okay, so in this loop, the field has value 2 squared 2 lambda, and in these loops, it has value 0. And you will see, okay, actually it's proved in the continuum that these values have to be different for loops which touch each other, and they alternate between these two values. So that's the second level of iteration. And then what we do is inside every of these blue loops, we sample again the CLE4, and we take the gray set to be our next cluster. So these new gray sets will be clusters which appear with a sign, actually, with the psi in the definition of the field. And all these gray areas here will be different clusters. So we have two stages. We sample a CLE4. Inside of that, we sample this additional two-valued set. And inside that, we again sample CLE4. And inside each loop, we sample again this set. And we take every second layer, which corresponds always to the carpet of a CLE4. So this is a third iteration of the process. So you get a fractal family of sets which somehow play the role of continuum clusters for the Ising magnetization field. Okay, so that's the statement of our result. It's pictorial. I hope you get the sort of the idea. And it's yeah, the technical statement is in our paper. So the takeaway is we have a new geometric representation of the Ising field in the continuum. It can be completely obtained from an instance of the GFF. So what are the differences with this one and the previous one? For example, in our representation, the loops are simple and they are self-touching in the representation of Kamiya, Gaban, and Newman. In both cases, the dimensions of these clusters must match the magnetization exponent. So it happens to be true that the dimension of the carpet of the CLE4 is the same as the dimension of the gasket of the CLE16/3. I don't know if it was realized before that this is the same dimension, but it is the same dimension. And the reason for that comes from the discrete, and it's that they both correspond to the Ising model. And how do we prove it? We actually devise a different percolation model for which we have the Edwards-Sokal coupling with the Ising model, and we take a scaling limit of that. And we use some recent results about scaling limits of double random currents, which were obtained in my paper with Hugo Dominil, Copan, and Wei Qian. Okay, so that's it. That's the statement. Are there any questions? I hope I have 15 minutes, right? I started 15 past, I think.
Hello, can you hear me? Yeah, you have 15 minutes.
Okay, thank you.
So I
So
have
maybe,
one question.
yeah,
I have one question. So I thought the other natural CLE to associate with Ising would be CLE3. So
right. The CLE3 is the collection of is the scaling limit of the interfaces of the Ising model. So there is so they are not naturally related to the Ising magnetization field. It turns out, though. Apparently, there is an ongoing work of Christophe Garban and his PhD student who will prove or have proved already that if you have a nested CLE3, then out of that you can read also you can read off the Ising magnetization field in some way. Sorry, I don't know the details, but okay. So there is a CLE3. Usually it's just a scaling limit of Ising interfaces, and it seems it's not the natural thing to do for the Ising magnetization field. That's why you go to FK, and then in FK you get CLE16/3. So that's my response. Sorry if it's not okay. All right, so I just want to tell you what the model is, and maybe that's going to be it for today. So we will devise a percolation model with the property that if I toss coins for its clusters, I get the Ising model, and the starting point is a random current model. So for this slide, I assume that the random current model is on the dual graph. It doesn't play really a role, but just to fix the notation, because that's how we will use it later. So the random current is just a random assignment of integers to the edges of the dual graph in this case. And with the property that the sum of currents around every dual vertex is even. Okay, so the set of sources, which is defined in this way, it's empty. So that's the classical random current, and the parameter is the same as the parameter of the dual Ising model, which is this J star. And this model has particularly nice combinatorial properties if you consider two independent versions of it. So it's classical to consider the double random current, which I will denote with this notation, and it's just the sum of two independent currents. And if you think about it, a sum of two currents is again a current. So that stays in the domain of a sum of two sourceless currents is again a sourceless current. So it doesn't make a problem here. And we can think of a current as a percolation model just by considering the edges where the value of the current is bigger than 0. Okay, so it is obviously very classical, and it has been very influential in the study of the Ising model. Very big results have been proved using the double random current model and the so-called switching lemma, whose one instance is this identity, that the square of the two-point function of the Ising model is the connectivity probability in the double random current model. Here I wrote G and J because the double random current model can be defined on any graph. So this was used not only in 2 dimensions, but in higher dimensions, and obviously you know that better than I do, probably. So this is the switching lemma. I just want to let you also mention one thing, is that this formula for the two-point function has a generalization for any set of vertices, which looks exactly as the formula I mentioned for the FK model. Okay, so for the general correlation function of Ising squared is actually probability that this double random current model belongs to this event FA that I mentioned before. And if you think about it, from that it follows that if you toss independent coins for clusters of the double random current model, you will get something which is called the XOR Ising model, which is a product of two independent Ising models, because this is the same as the correlation function of product over spins tau, where tau is defined to be sigma times sigma prime, and sigma prime are independent Isings. Okay. Square of correlations you interpret as product of correlations of independent models, you define a model which is product of independent spins. You call it XOR. And then this formula becomes exactly the same formula as we had for the Ising and FK model. And I told you that from that, it follows that if you toss independent coins on every cluster, you get the spin model. So from this switching lemma, you can immediately get the tossing coins on clusters of the double random current gives you the XOR Ising model. So that's one observation. Another observation is that the only important information for the current is just if the value is even non-zero or odd. So you can project the current onto two sets of edges. The first set of edges is where it has odd values, and the second where it has even and non-zero values. And for example, I have a picture here where I represented these even values by red and odd values by blue. So it's a current on the edges of the hexagonal lattice, and the odd values are represented by blue. And you can see that the odd values, they are always something which is called an even subgraph. By the sourceless property, I know that the edges where I have odd current, there must be always an even number of them around every vertex. So these blue ones, they create even subgraphs, which in this case, since we live on a trivalent graph, is always a collection of loops. So the probabilistic information of a current is basically encoded in just these two sets. And there is something very special about two dimensions is that I can interpret these blue interfaces as actually interfaces of the Ising model, which in this case lives on these faces. Okay, so this is a straightforward application of planar duality. So if I consider the Ising model with plus boundary conditions on the vertices of the triangular lattice, and then I draw interfaces between plus and minus spins, this will give me a collection of loops, which I denote by blue. And I keep this as my collection of loops. And on top of that, I sample an independent percolation with this parameter. And then I denote this by red. And I take the union of that. So I take the union of these two things. I claim that this has the same law as if I had a random current on my hexagonal lattice with the corresponding coupling constant. Okay, and moreover, the set of interfaces is the set of edges with odd value of current. So if to sample a current on a graph, it's enough to sample the Ising model on the dual graph, take its interfaces, this is the odd part of your current, and then sprinkle some independent percolation on top of that, and you recover the set of edges with odd current and the set of edges with even current. So given that, you can now play the game of having two independent models. So what happens if I take two independent Ising models on these vertices of the triangular lattice and I take the product? So if you take the product, you get the XOR Ising. So if you think about it, if you add two currents, the odd part of the sum will be exactly the symmetric difference of the interfaces of the two Ising models. So I have two Ising models, two independent sets of interfaces. I take their symmetric difference. This will be the set of interfaces of the product spin, and this will be the odd part of the resulting double random current. And on top of that, I must add a sprinkling, which is just the union of the two independent sprinklings. And if you do the computation of the parameter, so what is the success probability of two independent sprinklings with this probability, it becomes easier, and it is just e to the minus 4j star. So this is a lemma which tells you that you can get the double random current on your primal graph. Do I want it to be on a primal graph? Maybe I want it to be on the dual graph, sorry, as I defined it before. A double random current on the dual graph, what you do is you sample two independent Ising models on the primal graph, You take the product, that's the XOR Ising. You take this set of interfaces. This will give you a set of dual, this will give you a set of edges on the dual graph. This will be the set of edges with the odd value of the double random current. And now you have to decide where is this set of edges with even and non-zero value of the double random current. And this is just independent sprinkling of this parameter. I'm going fast. I know. I'm sorry. I just know. I want to make the statement, and then you ask questions to Lorca. I overestimated my abilities as I usually do. All right. So what is the theorem, which is the starting point of the whole paper? After we proved that there's lots of technical stuff, which I will not say anything about, but the starting point is the following. You consider a double random current model on the dual graph. You look at it as a percolation configuration. And now you consider its dual complement, which is the star operation. It's the set of edges now on the primal graph, where the double random current on the dual graph has zero current, basically. Okay, that's the dual complement. So this is the current, this is the percolation model, and now I look at its complement. So now I obtain something which is a subset of the edges of the primal graph. And the claim is that if I toss coins for this guy, I don't get the XOR Ising, as I said is the case if I consider the double random current itself, but I get the single Ising model, which may be surprising. Okay, this statement, as far as I know, in this form appeared for the first time in a master thesis of my student in 2021 of Ivan Heine at the University of Vienna. Statements to the same effect about the fact that the Ising interfaces are a uniform even subgraph of the double random current appeared in my paper on total positivity in the Ising model in 2017. And there are many statements in the literature which are related to that, which sort of a posteriori we found out that they are related. And for example, some of these statements in the papers of Sasha and Ron and Sasha and Piet are related to the statement, and we make the connections precise in the paper. Sorry, I don't have time for that now. But okay, I give you a proof of this statement in 4 minutes. All right, so let's consider a spin model and the set of agreement edges. Okay, so the psi of sigma is the set of edges where two spins are the same at the endpoints. And then small b, p is just an independent Bernoulli sprinkling with parameter p. All right, so as I said, the second direction of the Edwards-Sokal coupling says that if I take sigma according to Ising, and then I take the set of agreements intersected with an independent Bernoulli bond percolation with this particular parameter, I get the FK Ising. That's the Edwards-Sokal coupling stated in terms of these notations. Okay, now a claim is that our percolation model, which is this complement of the double random current, can be written in this following way. So it's the set of agreements of one Ising model and a second independent Ising model intersected with the Bernoulli sprinkling of a parameter which has 4 here instead of 2. And why it is the case? Because, okay, probably I didn't explain this well enough, but it comes from this fact here. I said that my current as a percolation model is a union of 3 things. It's a union of 2 independent Ising interfaces. So an Ising interface is an edge where the 2 spins disagree. So this is the set of edges where the spins disagree. This is the set of edges where the spins disagree. And this is some bond percolation with this success probability. So if I take the complement of that, because that was the double random current, and my model is the complement of the double random current, all the unions become intersections, the disagreement edges become agreement edges, and the success probability becomes the failure probability. So now my success probability will be 1 minus that. These sets of edges will be the agreement edges, and there will be a intersection instead of union. So that's this statement. Hopefully you can recover it looking at my notes after the talk. And then it turns out that this is a definition that you can actually apply irrespectively of if the graph is planar or not. So what I'm going to say from now on works on any finite graph. You take two independent Ising models on a finite graph, intersection of two sets of two agreement edges, and a Bernoulli bond percolation. It turns out that this has the Edwards-Sokal property with a single Ising model. And the proof is the following. So if you look at the density of two independent Isings, that just looks like that. And then you can simply rewrite it by using this tau spin, which is the product. So j times this sum of terms is equal to 2j times the indicator function that the product is the same on both endpoints times the spins of sigma. So what you get from here is that conditionally on taus, so you sample two independent Ising models, condition on the product. Conditionally on the product, the first Ising model is distributed as the Ising model with twice the coupling constants on the edges of agreement of tau. That's just exactly the same statement. So the first Ising model is distributed as an Ising model with twice the coupling constants on the set of edges where tau agrees. Okay, now I cannot all right. So that's the statement again. I will finish in 2 minutes. So sorry for that. So based on that, you can conclude that the right amount of sprinkling based on this FK coupling, the true FK Edwards-Sokal coupling, since the coupling constants are twice higher, and the right sprinkling has this 4j in it rather than 2. So this is the right sprinkling. Conditionally on tau, if you want to sample the FK model for sigma, and this is the right sprinkling that you have to do. And now the last observation is that, okay, if I consider this intersection of agreements, tau is the product of sigma and sigma prime. If I know that tau agrees and sigma agrees, it's the same as knowing that sigma and sigma prime agree. So that's the same set as that. And that's just the definition of my percolation process. So conditionally on tau, I know that this process is the FK2 representation of the first Ising model. And this holds conditionally on tau, so it also holds unconditionally. So all in all, if I sample this percolation model, which is intersection of agreements, intersected with additional sprinkling, toss coins on every cluster, it will give me a percolation spin configuration, which is exactly a single Ising model. And as I said, this is the starting point of our paper. And yeah, hopefully you get at least this coupling from this talk. And sorry for running over time.
Hello? Yeah, okay, let's thank Marcin. Any questions? Any questions on the Zoom? No? Okay, so...
Thank you, Marcin, for this very nice talk. So I understand that this new coupling where you get a single Ising model, this is new, right? I mean, you gave several talks in the past few months, but this one is, or am I mistaken?
Well, the way it's presented in our paper and here, I think it's new. the fact that the complement of the double random current model has the same law as this intersection of three things, I think that's a new observation, and it's important for our paper. And from it, you immediately get that this is the Edwards-Sokal, you get the Edwards-Sokal property. But if you separately look at this, not at the double random current model, but for example, at the just this general definition of these percolation models that work in any dimension, you can see these things in other papers, also in your paper with Sasha. I mean, you can see that they are the same percolation models. So they appeared before, maybe a bit hidden, not where this property was not spelled out as we spell it out, but they are over there. You can find them a posteriori. But the fact that they are related in the planar case to the complement of the double random current, I think that's yeah, we can claim that, and this is very important for our paper, this observation, because it gives you many nice properties for the complement of the double random current, which I didn't mention, like partial FKG and so on. But you can ask Lorca, he knows better.
Thank you very much.
Actually, I have one ultra naive question because I don't really know these things so well. So I vaguely have heard of the Miller-Sheffield coupling of the GFF with CLE4, right? And
Yes.
It seems very reminiscent of this. So,
yes. So
yeah.
yes, thank you. It's a good question. So for the CLE4 coupling of Miller-Sheffield, you consider the nested CLE4, and you just toss coins for every time you cross a loop, and then you add these sums up, and this has a distributional limit. I mean, you do it for finite sums, finite iterations, and then you take a limit. This converges to a generalized function. So this is a one type of theorems which has this form which is available, and we just provide another one. Also, you have in one dimension you have these theorems that you can decompose Brownian motion as the set of its excursions and independent coin flips. This is some classical result. I also forgot who exactly proved that. But yeah, our result is also of that type, but for a different field and in two dimensions. So these are called excursion decompositions result, I guess, in this field, and our result is just an example of that.
Okay, thank you. Any other questions? No, so let's thank Marcin again.
Thank you.